Hello and welcome everyone. So our discussion began by vectors, and then we covered some basics about linear algebra that was required to understand the linear algebra. And in the previous lecture, what we saw is, I'll just write the name. We saw geometry of these linear equations. So geometry of linear equations. So what I said there is the most important thing that I said there is, so whenever a linear equation is there, so first how you should think about it. There was a real world problem that was to be solved, and it somehow took a form of linear equation. Okay, as I gave example of house prediction, then we took the example of neural networks. So you will see humongous number of examples that take the formation, that take basically get transformed into the linear equations. Okay, so when you see these linear equations, there is a problem. Now how to think it geometrically? So I told you there are two ways to look at it. The first picture I call a row picture, and the second picture was the column picture. So in the row picture we said, okay, think it, let's suppose I'll restrict the discussion to 2D, and then you can just extrapolate it to 3D, 4D, ND, howsoever. And row picture was just take one equation at a time. If it is a line, you will just draw the line. If it is a other line, just draw these lines and sort of see geometrically. In the column picture, you take the columns. You take the columns of that, and then you see it as in terms of vectors in these coordinate systems. Okay, I won't go further into this detail because we have covered it in the previous lecture. So we have left our previous lecture on how to find the solution to the equations. Okay, I said there's a fundamental problem. So what is the fundamental problem of algebra? So fundamental problem was to solve linear equations. Solve linear equations. That is the fundamental problem that algebra solves. Okay. So now whenever I am solving something, think that there is a problem existing in real world which mapped to these equations. It's not that these equations came out of nothing and there is no application. So there actually was some physical system which was transformed into these linear equations. Okay, whenever we are solving that, we are finding the solution for that system. Okay, you can think about a machine learning problem. Let's suppose as we took in house prediction, or it can be a neural network, it can be some other function, but there will be some sort of physical problem which actually took the shape of these linear equations. Okay, now we'll see how to solve these linear equations. Okay, going to that now. So the first method that we'll see, there are a lot of methods by which we can solve this. We can solve these equations. The first method we'll see is the elimination. So elimination. Okay, and I'll write some equations, and before bringing in the linear algebra notation, I'll show you guys that how you use to solve when you are in +1, +2, and then from that we'll take it to the linear algebra. So let's write the equation. So equation, I'll write a system of equations. This is x minus 2y is equal to 1 and 3x plus 2y is equal to 11. Okay, these are equations. So in our childhood, how we call a method elimination. We said, can we somehow remove one variable? Because if you see, there are two variables. Okay, these are the two variables, and there are two equations we have. Okay, we have two equations and two variables. Now what's the meaning of the elimination? Somehow we want to eliminate one variable. We want to eliminate one variable, and then we can back substitute. If it was like this, let's suppose I had an equation like this. If I had an equation like this, if this x was not there, suppose this x was not there, if this was not there, then directly I could have got the value of y. I would have directly said y is equal to -1/2. But now this x is there. Okay, somehow I should do some mathematical trickery, and then I should get this x or y removed. It depends on me. What should I remove? Okay, let's suppose I want to remove this I want to remove this 3x. So how to remove this 3x? So I'll multiply this equation with 3. Okay, now the new equation becomes 3x minus 2y is equal to 3. Okay, because my goal now is that I have to remove somehow this 3x. So how can I remove this? If I make this 3x, then I'll probably subtract these equations. So this is 3x, and then I multiplied with this 3. This is actually 6y. Do keep an eye if I make some calculation mistake, because I'm speaking at the same time I'm making calculations, and I might make calculation errors. Do check for those. So now I have multiplied this 3 to the whole equation. I got 3x minus 6y is equal to 3. Now the second equation is as it is. Second equation is 3x plus 2y is equal to 11. Okay, now what can I do if I subtract these equations? Okay, if I subtract, let's suppose this equation, so this will become minus, this will become plus, and this will become minus, something like this. These things will cancel out. Okay, now I'll get 4y is equal to 8. Okay, so now if I calculate the value of y, so from this I can directly, I got this equation. Now I got this equation in one variable, and I have this equation, or maybe this equation, whichever you want to take. So now what I did is, if I now check the final set of equations, I got x minus 2y. I should write it with a better color. So x minus 2y is equal to 1 was the original equation. So when I did this elimination, I eliminated, okay, I knocked off this 3x. So what I got is, I got 4y is equal to 8. I got 4y is equal to 8. Yes?
Sir, you made a mistake over there, because minus 6, then we converted to plus, then there is 6.
Yes, it's 8y. Thank you so much. That's what I want you to pay the attention, so that if I make some mistakes, do correct them. Okay, this is 8y. Okay, because I don't have calculations done upfront, so I am doing it here. So if you see, x minus 2y is equal to 1, 8y is equal to 8. Now I got set of, again I have two equations, but now one of this, so I removed this variable. Okay, I eliminated one variable. Now it becomes easy to find the value of this y and then back substitute. Okay, this is called elimination and then back substitution. Okay, that's what we used to do in our +1 +2. Now if you see this, y is equal to 1. Okay, now I can take this value. So I got y is equal to 1 from here. I can take this value. I can say x is equal to 3. Okay, is it minus 3 or plus 3? It's 3. Okay, this is 1. So yeah, x is equal to 3 and y is equal to 1. These are the values. Okay, so if I substitute these values in here, it should satisfy this. So I got x is equal to 1, x is equal to 3, y is equal to 1. Okay, now you can see, just check these values. So x is equal to 3, 3 minus 2 multiplied by 1, this is equal to 1, yes. So 3 multiplied by 3 is 9 plus 2, okay, that's 11. So you got these things, that means our solution is correct. I just checked it. So now if you see this, what we actually make it, the initial equations were x minus 2y is equal to 1, 3x plus 2y is equal to 11. So we somehow transformed them. So by elimination, we transformed them into x minus 2y is equal to 1 and 0x, if I can write it like this, 0x plus 8y is equal to 8, something like this. Okay, these are the transformed ones and these are the original ones. Okay, this is the original. I suppose nobody should have any doubt till now. Okay, so if you now see this, can you see a peculiar thing over here? I somehow created this. So if you see, I created what's called as upper triangular thing. I won't call matrix right now because we'll go to matrix notation later. So my job here is to somehow knock off these variables. Okay, if I have, let's suppose now this x1 plus 2x2 plus 3x3, something like this, and I have a lot of equations like this. So my job is, initially I'll knock off these variables, I'll make them somehow 0, then I'll take this, I'll make this somehow 0, I'll make this. I want to make this upper triangular thing. Okay, if I have more equations now, we'll go to that. But here you can see that I somehow got this upper triangular sort of matrix, which we will see shortly. But my job initially was to reduce these variables, so that I just got if I got a value for one variable, and I'll keep on back substituting, and that is, I'll get it by here. So for the last equation, I'll have all the zeros except the last entry, and for the n minus 1th row, I'll have n minus 2 entries, which will be 0. Okay, and then 2 entries which will be non-zero, something like that. Now let's take it to algebra. Okay, so in order to take to algebra, so what I can do is, I can just write it like this. I can write x minus 2y. Okay, let me again see the equations. X minus 2y is equal to 11 is 1, 3x plus 2y is equal to 11. Okay, so now how I can do it is, I can just write it like this. So 1, 3, minus 2 and 2. Okay, and this is, and then I have x and this is y, and this is equal to 1, 11. So it took a form ax is equal to b. This is A, coefficient matrix, then this is x and this is b. Okay, before going ahead, I'll first show you the column picture and the row picture of this when we had the original thing and we transformed. So basically, if you imagine it, we want to find a solution. Okay, we want to find a solution. The thing was like this. We had two lines. I'll just restrict myself to lines. You can extrapolate it to planes. So my first line was something like this, let's say. Okay, second line was something like this. Okay, so here is the point. This point is the point of intersection, which is the solution. So what I want to do by elimination basically is, I want to knock off one variable from the equation. So somehow I want to transform this line. Okay, this second line, let's make it red line. Okay, and let's make this point over here. Okay, so what I want to do is, I want to make this line straight somehow, that I should make one variable 0. So if you see this point over here, if you see this line, so there are some x comma y values, particular values. So if I make this line like this, if I make, let's suppose this line like this. Okay, still the intersection point is same. Intersection point, I did not change that, but I somehow transformed this so that if you can see this, now the value of one thing remains. Like if you see this line, so here it has a value of y, throughout this point, let's suppose. So if you see, if I want to measure this, so I'll go to this and I'll go to this. So I made somehow the line straight. Okay, I made the line straight. It is parallel to x-axis over here. Something like this. Let's see it with the code. It will be more clear by that. So basically, what I want to do is, in order to knock off one variable, in order to remove that variable, I just want to make this line a little bit straight. If you see that, I want to make it straight so that I can cancel out the effect of one variable. Okay, let's see that in the code with the same equations. Give me a second. So now I'll write the code for these. We have two equations and we'll write code for them, and we'll write before elimination and after elimination. Okay, I want to show you what happens. The first picture that I'll show you is row picture. I'll just plot these lines. Okay, so now the first standard stuff is I'll import this matplotlib and I'll import NumPy. Okay, and these are the standard import statements that we have been doing since day one. Now what I'll do is I'll create some x values, because x is my independent variable. I'll create some x values. So x value is equal numpy.linspace minus 10 to 10, some 400 values I'm creating. Now what I'm doing is, if you see the equation first, okay, so now if you see equation first, I'll get the values of y like this. If you can see this, so y is equal x minus 1 by 2, and for the second equation y is equal 11 minus 3x by 2. If you just rearrange the terms, you will get the values of y corresponding to each equation. I wrote them here over here. So I'll say y set 1 and y set 2. I'll just code them now. So this is just commented out. So I'll again paste the same thing. So I'll say y set 1, this is my x minus 1, so x minus 1 by 2. This is the y value for the first equation, and this is the y value for the second equation. That's what I coded over here. Okay. Now what I can do is I want to plot it. If I want to plot it, so let's create two figures. In the first plot, I'll plot the row picture, and then in the second, I'll plot the column picture. Okay, that's why I'm saying 1 by 2 and give me two axes, and this is the size. What I'll do is I'll first plot this. Ax is 0, plot this. Okay, this is my ax of 0, plot x values and set 1, and then I'll plot the second. I'll plot the second line. Okay, this is the second line. This is the equation of the first equation. This is the first equation, and this is the second equation, and this is what I'm plotting the line, because I have this x values and I computed the y values. Okay, now I'll just set up this graph. Okay, set up this graph things to just make these legends, and this is the first set of equations. And I think color, and this is color. This is for horizontal and vertical axis. These are my axes, and should we give them the color? Okay, I think it will take some default color. Let's see. So if you see now this, if you see it, okay, this is what the sort of row picture looks like. So they intersected at this point. Okay, this is these are the set of equations I had. So I had this equation. So now if I transform them, okay, if I transform these equations, so what should happen is I basically transform this equation. So what is the transformed equation? It was 8y is equal to 8, that equation. I transformed the second equation. Okay, let's go to that. I transformed the second equation. Let's now write the transformed equation and plot that transformation over here. So I wrote that. So now what I'll do is I'll plot these equations over here. Let's take this set 1. So set 1 will remain the same. So equation y1 set 1. So this will remain the same. So this is set 2 equations rather. So set 2 for this, the first equation remains the same for both. And now the second equation got changed. In the second equation, what we did is, so second equation basically was 8y is equal to 8. So that means y is equal to 1, something like that. So I'll say y is equal to 1. Okay, so this is set 2 equations. Okay, y2 is equal to 1, and x is getting varied, but we put a constant value. That's what I said. I have to make one of these lines as constant. So I'll either have it parallel to y-axis or parallel to x-axis, so as to make one value constant. Okay, and then I'll plot it again. Nothing major in plotting. So again, I'll copy the same code that we wrote over here. Okay, now you can see the second plot is ax of 1. It will select this axis and it will say plot this x values, but this time this is set 2. Set 2 has this equation. Okay, x minus 2y is equal to 1, and the second equation was 8y is equal to 8. Now I put that y is equal to 1. So this is the second set of equation. Now we'll see how it transformed this. Can you see it made it parallel? Answer did not change. So if you see in the both of these plots, so over here this was the intersection point. So on this line, so somehow I transformed this line. Okay, so I want to transform line. It's like something you are having this point and you have nailed the point, and you can rotate both of these because the solution won't change. Okay, so because you want to find this point, the intersection point. Okay, somehow if you have these two things, you have this cross and you nail the point where they intersect, and then you can move them freely. Okay, and whichever is comfortable for you, you can move them in that. So in here, our most comfortable thing was to make it independent of variable, remove that variable. So in here, what we did is we removed the x. Okay, so in here if you see, we made y constant and we removed the effect of x. That's why we got this 8y is equal to 8. That's y is equal to 1. That's why we got this over here. If you see this, okay, this over here, y is constantly equal to 1 now. So if you saw over here, y is equal to 1. Okay, this is 0.0 and then 2.5. So y is equal to 1 over here. For this point, y is equal to 1. Okay, then if you see the x, okay, x is getting varied. So if you see x is equal to 3. Okay, if you see this is 2.5, I think this is 3. So if you see this point, this is a little right to 2.5, this is 3. So can you see this? So it is something like this. I don't have a second pen over here, but I hope you got the point. So if you see, these are the two lines which were intersecting, and this intersection point was the solution to the equations because it satisfied both the equations. Now you nail it down, you put a nail inside, okay, and then you can rotate these things freely because you are not changing the solution. You might change the lines, but your point is to find the solution, not you don't worry about the lines now. So now you want to find somehow a solution. So that's what you are doing is you are basically just rotating these lines such a way that you get answer easily. So what was the easiest route? Easiest route was to make either you can make this yellow line or orange line straight, that is you make it parallel to x-axis so as to keep the y value constant, okay, and this will knock off the x value. Or you can do it other way, you can remove the x from the first equation. You can make this equation parallel, and this can be also made parallel to y. So there are a lot of things that you can do over here, but I think you got the point. Questions? Yes. Okay, just to remind you again, so if you see these two lines, if they have a solution, so they will be intersecting at a point, okay, and then you want to freely rotate them, but just keep in mind that you have to stuck some nail into that, and then you can rotate them freely and according to the ease. So what I'm saying is there are a lot of possibilities how you can do it. So easiest possibility is either knock the x or knock the y from any of the equations. That's either rotate this first equation, rotate the second equation, basically the line, and whatever suits you, and you can find the solution accordingly. Okay, this was the row picture. So how to imagine it when you are solving, basically now you can extend the solution to 3D. Okay, then you can think in 4D. You can sort of pretend that you can imagine in 4D, but it's very difficult. But you can do the same thing with planes. Now you have 3 planes. Okay, you want to move the planes around. You want to move the planes in such a way so that you knock off the different variables, and you basically make one parallel to x-axis, one parallel to y-axis. Okay, and then maybe other you keep it as it is. Okay, that's what is the meaning of this lower triangular thing. So if you see in this, what's the meaning of lower triangular? Whenever you knock off something, you basically make it parallel to one of the axes. Okay, I knocked off this x variable. I made it parallel to x. Okay, if I knocked off the y variable over here, okay, I'll make it parallel to, let's suppose, y. Okay, similarly you can think in the 3D. In 3D we'll have 3 planes. Okay, when we have 3 planes, so when you knock off the first variable, when you knock off, let's suppose there we'll have something like this: 1, 2 and 3, 1, 2, 3, 1, 2 and 3, something like equations will be something like this. Okay, we'll have these 3 terms equal to something. So we want to knock off this. So what will happen? It will become, so you are removing 2 values. Okay, it will become parallel to probably 2 axes. Okay, and then you are removing this. It will become parallel to 1 axis, and this thing will probably be non-parallel in most of the cases. And now you can see that you somehow can find the solution. You can from here back substitute into this, and then whatever solution you get from here, you back substitute into this, and you back substitute to get the values. Okay, but in here I suppose that you got the understanding how to think about these equations when you are thinking in the row picture. So in the row picture they intersect somehow, and you are freely moving them, but just underpinning this point where they intersect. Okay, any questions on this? So what I'm saying is the question asked was can we make it parallel to either x-axis or y-axis? The answer is thus you can make it. Why? The goal is to knock off one variable. If we have 2 equations, 2 variables, so 2 equations, let's suppose we had x minus 2y is equal to 1, and we had 3x plus 2y is equal to 11, something like this. Okay, so we knocked off this variable. Okay, once we knocked off this variable, okay, so this became 8y is equal to 8. So this became a line parallel to x-axis. Okay, because we want to remove the effect of x. That's what we want to do. We want to remove the effect of x. You could have done it the other way. Okay, you can have done it other way around. So you could have just knocked off this y. Okay, and did something, knocked off this, and this will have been a line parallel to y-axis, and then you could have removed the effect of y and just kept the x. Okay, howsoever you solve it, but the only thing that you have to care about is, so you can rotate these lines any somehow. So these lines are like this. So you have one line like this. Okay, you have other line like this, and this is the solution if they have a solution. Okay, and then what you can do is you can rotate them in any possible way, but just keep this thing hinged. Okay, keep a pivot. Okay, pivot thing is like what you can leverage over. So this is a pivot, just nail it down and then move these lines freely, because you are not changing the solution. You might change the line, but solution is not getting changed because this point is remaining the point. And howsoever you want to do it, you want to make this line parallel to x-axis, do that. You want to make this axis parallel to y-axis, do that, no problem. The point is to find a solution. But what was the most obvious thing? Most obvious thing to was to make it upper triangular. So we had x minus 2y is equal to 1, 3x plus 2y is equal to 11. This was the original, and transformed equations were x minus 2y is equal to 1, and we knocked off this. Okay, we made it upper triangular. So that was 8y is equal to 8. And we got 0 over here. Basically what we are doing is, so if you keep on doing this, you are making each equation parallel to one of the axes. So now, as I said in this, just to remind you, so if we have 3 equations, 3 variables, so now we have these planes. Okay, these planes, let's suppose they have a solution, they are non-collinear. So in that they are intersecting at one point. So when you are knocking off these 2 variables, you are basically making it parallel to 2 axes. Okay, you are just removing the effect of 2 axes, because we have 3 axes, x, y and z in our coordinate system. And when you are knocking off this, you are making it parallel to 1 axis. Okay, because when you are making it parallel to 2 axes over here, you can directly back substitute the values, and then from this value you can substitute these values into this, and then from this you can do it in this. And that's why we have to make it an upper triangular matrix, something like this. Okay, basically what you try to do is, the last equation will be parallel to all the axes except one. Okay, it will be parallel to all these planes, or whatever you call them, axes, except one. And then the second, let's suppose this will be parallel to 1. Okay, basically if we have n dimensions. How to think about this? So if you have n dimensions, so the last equation, because we knocked off all the variable, you just kept one variable over there. That means it is parallel to all the axes except last one, except 1. So we have n minus 1. So here it will be parallel to n minus 2. It will be parallel to n minus 3. Okay, if we have n dimensions. So in 2D case, so when you knocked off this variable, so when you had this, so this was parallel to 1. So because we had 2 dimensions, this last was parallel to 1, and this may not be parallel to any. Okay, if we had 3 equations, last equation will be parallel to 2 of the dimensions, and n minus 1 penultimate will be basically it will be parallel to 1, and the last the first equation, basically it may not be parallel to any of the dimensions, any of the axis lines. Is that clear? Is that clear? Yes, ask the question. Okay, so in the elimination, what I said is, if you have this equation, we had the equation x minus 2y is equal to 1, and then we had some value, I think 3x minus something was equal to 11, so I wrote it over here. So 3x plus 2y is equal to 1, something like this, is equal to 11, something like this. So when you are removing a variable, so basically what you are doing is eliminating the variable. You are not making this variable 0 in that plane. So if you see the geometry, of this line, okay, I am restricting this into a line, and you can extrapolate it to the planes and hyperplanes. So when you are removing this, knocking off this variable, it basically is making it parallel to one of the axes, making this value, basically this y is now getting constant value. This y is getting constant value, and this x value is now getting varied. Okay, this x is getting varied, or if you see over here, this x is getting varied, and y got a constant value. You fix the value y. Okay, so that's why you are basically eliminating the effect. So if I say elimination, basically means remove or eliminate the effect of variables. Okay, and how to write it mathematically? You just knock off that variable, you just remove this variable. That's how this value gets, because you got a constant value for this. Okay, and then if you see you let this x vary. Okay, you are eliminating the effect of these variables, and you can project the same thing to high dimension. Okay, this was the row picture. Okay, again, to just demonstrate this, so we had line like this. Let's say line was this, and the line was like this. Okay, and this was the solution if solution existed. Okay, what we said is, we are interested in solution, we are not interested in lines. So now mathematics of power, you can rotate these lines anywhere, you can rotate both of these lines, but just make sure that you hinge this value, you pin it somewhere. Okay, and so that this solution is not moved. Okay, the solution remains as it is, and then you can move the lines according to your convenience to find the solution. And one such method was elimination, which I explained, so that you get an upper triangular matrix, and then from upper triangle you do the back substitution. Now this was the row picture. Now let's see column picture. Let's see the column picture. Okay, writing the same equations, the equation is x minus 2y is equal to 1, and 3x plus 2y is equal to 11. Okay, now after we eliminate, once we knock off this, so what we got 8y is equal to 8, something like this. So this is the first equation, and this is the second equation. Okay, now what happened in the elimination? What I'll do is, I'll have to now write it somehow into these column vectors. Okay, into the column vectors that we had. Okay, let me directly go to the code window and show you that. I think I have the code window open here. This was the row picture. Let's now have the column picture. Okay, I'll write all the columns. So I'll define all the vectors that are here. So if you see, this v1 vector is 1 comma minus 2. Okay, and I should actually change, this is 1 comma 3, 2, and then I have 2 comma 2 and 1 comma 11. These are the vectors. Let me just write them. I don't think these are right values. So if you see this, so let me bring the pen. So the equation that we are at is x minus 2y is equal to 1 and 8y is equal to 8. So now there are three vectors. One is this 1, 0, this is 1 and this is 0, and then we have minus 2 and 8, and then we have 1 and 8. Okay, and these are the two things that are of my interest, 1, 0 and minus 2, 8. Okay, that's what I'll code. So let's call this v1 is equal np.array, and it is 1, 0. Okay, I'll write this 1, 0. This is my first vector. Okay, and after I did the elimination part. Okay, and I have v2. Okay, v2 was np.array, and this was minus 2, 8, minus 2 and 8. Okay, this is after the elimination. Okay, I'll write it over here after the elimination. So I should write av1. So this is av1 basically means after elimination, and I'll write before elimination also. So this was after elimination, and what were the equations before the elimination? So these were the equations before the elimination. Before elimination, and I'll also change the values. The values were 1 and 3, I think 1 and 3. This was 1 and this was 3, and this was minus 2, 8. I think it remained the same. It remained the same. No, this was minus 2 and plus 2. This was minus 2 and plus 2. I think was it 6 or something? What was the value, actual value? Can somebody remind me the equations? What were the actual equations? Is this the right thing? I doubt it, because no,
2y is equal to 1, 3x plus 2y is equal
okay.
to 11.
Then it is 2. Okay, then this was before we did the transformation, and this was after we eliminated the thing. Okay, now these are the 4 vectors. Now what is the output vector? This is the output vector. I'll write out vector. So out vector was 1, 11. Okay, so the initial out vector, I'll say initial out vector when we did not perform the elimination. The initial vector was np.array, and it was 1 and 11. 1, 11. And after we did this, so it was 1, 8. Yes, so it was 1, 8. So the elimination out vector, this was 1 comma 8. Okay, I hope you can verify the calculations. Now what I want to show you is basically what I'll do is I'll plot these things first. I'll plot this vector, I'll plot this, okay, and the input vector. Okay, if I see this, so let's say I'll plot it. So if you see this, I just plot this. So I'll say before bv1, and this is before, and this is before v2. Okay, let us put these things also to just configure the limits. I think you should be able to get it now. Okay, these are the two vectors which we initially had. Okay, so I actually also want to show you the out vector. So this is 0, 0, and this is the input out vector before elimination. Okay, I'll write it. This is output. Okay, not write the equations, and this should be actually given the value. This was 1, 3 and minus 1 comma 3. Oops, 1 comma 3 and minus 2 comma 2. Minus 2 comma 2. Okay, and this is the output vector, which was 1 comma 11. 1 comma 11. Now if you see this, okay, and let us not limit these things. So let us not limit this because we have this 11. Oh, it's going haywire. We should limit, but we'll keep the values because we have 11 values. So we'll keep it till 11, maybe till 12, so that it appears nicely. And now you can see this. Okay, I'll just remove this. So if you can see over here, okay, maybe we should change the color of resultant also. Not, it is not actual resultant. So let's put the color. So this is some red color. So this was our one vector, and this was the other vector. Now what you basically want to do is you want to see, okay, what combination to take to reach this. Okay, so this is the vector that we have to reach. Okay, this vector is the vector that we have to reach. Now these are the vectors that we have to take, this vector, this green and this blue vector. So what linear combination should we take so as to get to this vector? Okay, so as to get to this vector. So what is it saying? It is saying now if we transform it, okay, so we should take 1 of this, 3 of this to reach, let's suppose this vector. I think the solution was 1 comma 3. That means we have to take 1 of this green vector and 3 of this vector to reach this vector. So this was the initial answer. So what this column picture tells us is that, so whatever combination you took initially, you took 1 of the one vector and 3 of the other vector to reach this vector. So when you did the transformation, it should be the same. You should again mix the vectors in the same proportion so as to get the final vector. Okay, let's do that. Let's again make one more diagram over here. I could have made it sidewise, but this will be easy. That I can just paste and copy paste. So this will be after this, and this is after this. Okay, this is after, and again this is after. Now you saw everything got transformed, and this is elimination and this is elimination. Okay, if you see this, okay, now you saw all the vectors got transformed over here. So here also vectors got transformed, but the solution remained the same. Okay, you will take 1 of this and 3 of this. Okay, if you take 3 of this, you will probably reach over here. Okay, you will reach over here, and then by the addition law you can clearly see that this is the solution. So you take 1 of this green vector, okay, 1 of this green vector, and you take 3 of this blue vector to reach this. So before transformation, after transformation, nothing changed. So whatever you transform, so the row picture tells us that you should pin that point where they are intersecting. So here, what is the column picture telling us? Column picture is telling, before we transform these vectors, whatever proportion you use, combine these vectors and you landed at this output vector. So when you perform the transformation, the same proportion should be preserved somehow. So here if you see, the same proportion got preserved. So you take 1 of this vector and 3 of this vector to land at this red vector, okay, by using the addition. Now in this, you take 1 of this vector and 3 of this. If I just show it, I think it is clearly visible on the screen. So this is second and this is third of this vector. So you can clearly see that by the parallelogram law you can reach here. So again, row picture tells you pin that point where they intersect, and then you can rotate the lines. Okay, in this, how should be the rotation done? The transformation or rotation should be done such a way so that the linear combination should remain the same. Initially we were taking 1 of the green vector and 3 of the blue vectors, and after transformation same thing happened. You can see that we took 1 of the green vector and 3 of the blue vectors, and so as to land at the final vector. So is the row picture and the column picture clear now? We just hiding this code window for a while. So now what you can see is, here it was a good case. So in the example that we took, the lines somehow intersect at a single point, and we can see the row picture and the column picture. But what if there was a failure case? Okay, by failure I mean there is, let's suppose, no solution. Okay, by failure I mean there is no, I'll write equations which have no solution. X minus 2y is equal to 1. How to make it a no solution? So I'll say 3x minus 6y is equal to 11, something like this. Okay, now if you solve these things, if you knock off one variable, what you will get is, you should get, let's suppose we remove this. Okay, if you remove this, so you will get 0y is equal to something. Okay, 0y is equal to some non-zero value. Okay, so this will be non-zero value over here. So because when you multiply this with 3 by elimination, so this will be 3x minus 6y. Okay, so when you put this, this will be minus, this will be plus, and this will be minus. So 11 minus 3, this will be 8. Okay, 0y is equal to 8. Okay, now if you see this in both the pictures, I'll just make the picture. Now you will have to think on your own. Okay, so now you can see that before the transformation, if you did it, after we performed the transformation, there was no point actually. So you make them parallel. So I'll show you that picture also. Let me just copy this whole code and I'll explain the code. These are the two column pictures, and I'll show you this. So now if you see this is our y1 line and y2 line. Okay, and now I am showing you the columns. Now this is the picture. So you can see this clearly. So this, okay, and this is a line, and second line, when you transform, it vanished. Okay, there was no second line. That basically means these lines were parallel initially. They were parallel. Okay, now in this, now the important aspect over here, you can see clearly over here. So these things don't intersect. Okay, over here these lines do not intersect, and they were parallel lines. And now you can clearly see that there was no solution. But in here, if you see, this is the most important thing. So I wanted to get an output vector. Output vector was 1 and 11. Let's make that also. Output vector is 1 and 11. if you see this column vector, this was 1 3 initially, and then we got 3 minus 6. The output vector that we wanted actually was 1 comma 11, np 1 comma 11. Okay, now I'll also plot this. Here that is. I'll say out. This is out. This is again out. Names will be here and there. Pardon me for that, but I just wanted to show you this. Now you can see this. Oops, yeah, this thing is not good. Let me check again. Limit it to minus 10 to 11 so that it is visible at least. Yes, now you can see it is visible. Give it red. Okay, so this is the vector that we wanted to reach, but you can see this vector was from this. So this was 1 comma 3. Let's suppose this was our 1 comma 3, and this was our vector 2 comma 6. This one, okay, minus 2 minus 6. This was minus 2 minus 6. This was 1 comma 3. Now we have to take some linear combination in order to reach to this vector. Okay, in order to reach to this vector, we have to take linear combination of these. But you know that the span of these two vectors is where they can reach. The span is only this line. Okay, span is this line. They are restricted to this line. So if you see, this is the span. Okay, they cannot reach this. This vector is out of the span. So this is not in the span of these two vectors. No matter what linear combination you take, you can never reach this vector because the span somehow is restricted on this line. So you just have a straight line over here. Okay, you have a straight line from this. The span is this because you can just scale the values. If you take any linear combination, it will just stretch the line or squish the line. The span is a straight line like this. Span is from here. Here you can just extend these lines, but no way you can reach this vector. Okay, that means there is no way of achieving this vector by using these two vectors. Okay, by using this orange and blue vector, there is no way of reaching this red vector. Why? Because you cannot take any linear combination to reach that. That means it does not belong to the span because the span is the line and this vector does not lie on that line. Is that clear? This is the failure case where there was no solution. Is it clear? Now we'll do a discussion to 3 equations in 3 variables because we have seen 2 equations in 2 variables and we have a line in that. All the things that we have visualized will apply similarly in here, but it's difficult to make the 3 visualizations and it looks too cluttered. But I hope that you can extrapolate it based on whatever we saw in the 2D. Okay, let's write the equations. So if you see 3 equations in 3 variables, so I'll write a set of equations. 2x plus 4y minus 2z is equal to 2. 4x plus 9y minus 3z is equal to 8 minus 2x minus 3y plus 7z is equal to 10. Now the first thing is we have to use the procedure of elimination. So what is the elimination? So if you see, I can take coefficients out. So coefficients are 2, 4, minus 2, 4, 9, minus 3, minus 2, minus 3 and 7. Okay, and these are my coefficients of these variables. And then I have this x, y and z. Okay, and then I have 2, 8 and 10. This is my b. Okay, the succinct representation is a x is equal to b. Now I need to do the elimination. So how do we do the elimination? So basically we take this element, initially we will take this element and make all the entries below it equal to 0. So why? Because we want to make it upper triangular matrix. We want to change this ax is equal to b to ux is equal to some c. Okay, because whatever transformations you apply over here, the same things will get applied over here. That's why I wrote ux is equal to c. So if you see these elements, so these elements are called as pivots. They're also pronounced as pivots. So I'll call them pivots. So now you see this is a pivot, and below this you have to use this this row and multiply it with a certain factor and make all the entries below it equal to 0. Okay, and then you will go to the next row. So you will take this element. Basically, this will be pivot. If it is non-zero, then only it will be considered as pivot. Pivot never will be a 0 entry. If it is a 0 entry, you will have to swap the rows. Okay, why swap? Because you want to make the pivot as non-zero and what are the below elements and you want to make them 0. Basically, you want to get an upper triangular matrix. So over here, you want to get a matrix like this. You want to get a matrix in which this entries are 0 and rest of the entries are non-zero. This is what is an upper triangular matrix. Upper triangular matrix. Okay, again to remind you, we have ax is equal to b. So what we want to do is we want to get it like ux is equal to c. Okay, so this won't change the solution. Okay, solution will remain the same. So I want to then find x, but this u somehow will be an upper triangular matrix. So what is the advantage of upper triangular matrix? So once we get the upper triangular matrix, we can take these entries and do the back substitution, and it will be very easy to do back substitution once we have the equations in upper triangle. Now let us do elimination on this. So in elimination, if I tell you the steps, so you can swap the rows. So I'll just write the rules for elimination. They're pretty easy to guess these rules because we have done this in earlier equations which were in 2 variables. So the first rule is you can multiply a row with any non-zero number, So you can multiply it because you want to multiply the whole equation. Basically, you have the whole row and you want to multiply it with that non-zero number, and you want to subtract it. And you can again do the same thing. You can multiply or divide. So whatever you want to do, you can multiply or divide. Similarly, you can add or subtract a row to another row. So each row, if you see, is an equation. Basically, it is representing an equation. So when you are doing a substitution equation, now we just did one thing. We just took these coefficients out, and we have the numbers. We have these coefficient matrix, and we are doing these transforming on the coefficients. We can either multiply, divide by a certain factor so as to maybe subtract, because we want to get these below entries the pivot equal to 0. Okay, so if you see, this is my first pivot and this will be my second pivot, and pivot is always non-zero. So now if you see this, so now you can also do one more thing, that's you can swap the rows. You can swap the rows. Why is swapping needed? Because let's suppose sometimes you might have a case where the problem is that you will get 0 entry in the pivot, but below that entry there will be some non-zero entry, and you want to swap that. Okay, you want to swap because, as I said, pivot is not equal to 0, and that is not accepted. Okay, and pivot actually should be non-zero, so that below it, the entries below it should be made 0. So now coming back to the equation. So okay, so I'll write the equation. So equation is 2x plus 4y minus 2z is equal to 4x plus 9y minus 3z is equal to 8 minus 2x plus 3y plus 7z is equal to 10. So these are equations that we have. Now we want to perform the operation. So the first step will be the step 1. Okay, because I'll use this as my pivot. So this is my pivot. Okay, now I want to make this entry 0. So if I directly add this, so if you see this equation 3, if I add equation 1 to it, obviously this entry will be knocked off and it will become 0. But to get this equal to 0, I'll have to multiply this equation with 2. So multiply equation 1 with 2. Okay, multiply by 2. I should write by 2. Multiply by 2, and then what should you do? And you should subtract it. You should subtract equation 1 from 2 and subtract equation 1 from equation 2. Okay, by that I make sure that this entry becomes 0. Then this is the first step. And now the second step is, once I got this entry as 0, okay, then the second step will be I'll subtract this, let's suppose, or maybe I'll directly add. Okay, I'll add these two equations. So step 2 is, okay, because now I want to get this entry 0. I first was getting this entry 0. Now I am getting this entry as 0. So in here, what should be step 2? Step 2 is add equation 1 and 2. Equation 2. So what will happen is you will directly get this as 0. Okay, because this will be equal to 0. So you will add this equation and you will add this equation 1 to equation 2. So that is, you won't make this entry 0. Now step 3 is, now you will have new, and now let's suppose this will be some other number. So you want to make the below entry 0. Okay, the step 3 will be to subtract whatever the second new entry from the, so you have to subtract this new equation, whatever this new equation is, from this, and you have to multiply with a certain factor. If this is not 0, if it is 0, you will have to swipe these. You will have to sorry for the swipe, you will have to swap this. Okay, so now what will be the goal? So if you see, so you will get something like this. So you got 2x plus 4y plus minus 2z is equal to, and this is the original equation that I am writing. This is 4x plus 9y minus 3x is equal to 8 minus 2x minus 3y plus 7z is equal to 10. So this is the original set of equations that we wrote. Okay, now once you transformed it, so what is the transformation? So that will look like this: 2x plus 4y minus 2x is equal to 1y plus 1z is equal to 4, and 4z is equal to 8. So this is ax is equal to b, and this is the transformation ux is equal to c. Now from this you can do the back substitution. You will get the values of y is equal to x and y and z, x, y and z. These are the values. So I'll directly write the values without computing. You can just test it. X is equal to I think it's -1, and this y is equal to 2, and this z is equal to 2. So these are the values. Okay, again same column picture and the row picture. If you see in the row picture, these are the planes and they are basically intersecting on this point. Okay, second thing, if you see the row picture, if you see sorry, in the row picture, this is the picture that they'll be intersecting on this on a point. in the column picture, what will happen is if you take these vectors, okay, if you take this column, so basically this column over here, and if you take this column, so you will take a linear combination of this, you will take this, 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 the linear combination of this will give you the C, okay. Now basically what we want is we want to get the upper triangular matrix, and so we want to have AX is equal to B, and from this we want to get UX is equal to C, and this should be done by different transformations, and then you can solve it, solve the X, and you can get values of X1, X2, whatever, or X, Y, and Z, something like this, okay. But the more important thing is to code it. Now you know the theory. If you know the theory, so behind the theory you should know how to translate these things in the code. If you know that thing, then only will you understand the things better, and you have a good grip on the coding. Okay, let's go to the code window, and I'll write the code. Okay, so let's do that. Okay, here comes the code. Now I have shown you the coding window. So now the first thing that we do, will import NumPy. Okay, so what does the NumPy do? Because all the functionalities that we'll do is by using NumPy. So we'll just import NumPy as NP. Okay, let's import this. So import NumPy as NP. I'll just run it. So now what I'll do is I'll write definition, and then I'll write elimination method, and I'll write it as a matrix. Okay, because this takes matrix as an argument. The first thing that I want to do is I want to calculate, I want to take basically the number of rows and number of columns, because I'll have to iterate through all the rows. I need to get rows and columns from that. And how to do that? So if I need rows and columns, okay, in NumPy, how to do that? So we'll just write matrix dot shape. So if you have an NumPy array, so we just write shape. So matrix dot shape. So what it basically does is it will create a tuple which will give me rows and columns. So I have just sort of, if you see, I have just opened them up because it's a tuple, and I just use this rows and columns, and accordingly it will be assigned. Now the first step that we will do is we have to perform forward elimination. So in order to do the forward elimination, we basically, the goal is to find upper triangular matrix. So for that we must find the right pivot first. Okay, so we should go through all the rows. If you have a matrix, we should go through all the rows. I'll parallelly keep the matrix with me. So the matrix, if I write it correctly, this is the matrix that we have. So 2, 4, minus 2, and 4, 9, minus 3, and then minus 2, minus 3, and 7. This is the matrix. Okay, whatever operations you do on this A, X is equal to B, I am saying you do transform on this A, this is the A, and the same transformation should be done in B. Okay, whatever you get in the B, and then you can find the values of X. So once we code it, we'll basically get the augmented matrix, and we'll just stack on one more column over here, one more column, that is the B column over there, and whatever operations we perform on this A, we'll do the same operations on this B. Okay, now let's go back, and I'll write this. So we have this shape, and we got this. The first step of this is I want to go through all the rows and find the pivoting element. Okay, so how to do that? So I'll say this is finding the pivot element. Okay, so how to do this now? So first I'll say for I in range of, I want to go through all the rows, so I am checking for all the rows. For I in range of all the rows, so what I want to see is I want to go to the pivot element. So what element is pivot? So usually if you see over here, so this is, let's say this is 1, 2, and 3. This is again 1, 2, and 3. Pivot elements are always diagonal elements. So diagonal elements have entries 1, 1, 2, 2, 3. That's I. Okay, so if you see, I can write check the element at diagonal, basically the pivot element. If it is 0, if it is 0, then I have to swap. If it is not 0, then I can move ahead. Okay, so I'll say if matrix of I, that is the diagonal element, the current diagonal element, the current row I am at, if it is equal to 0. Okay, that means I need a swapping. So how to swap? So I need to swap it with the below rows, but that below row, the element below that pivot, that should be non-zero. So let's suppose it was 0 over here. Let's say if this 2 was 0, okay, and if this was 0, I have to swap it with 4, because 4 over here is non-zero. So it was 1, 1. So okay, now what we are doing is this is our I, number of rows is our I, and this columns is our j. So I am keeping this I as constant. Okay, if you see this, but I'm changing the j. Okay, j is basically going through these. So that's why what I'll do is I'll write this ij. I'll just swap this with ji. Okay, I'll have to swap these rows. So how to swap? So here I'll say if this is the case, so swap the rows. Okay, but before that, you should be sure that the entry that you have, the entry that's beneath the pivot element is non-zero. So how to write that? So we have written this if this matrix is equal 0, then we should again run one more loop for j in a range of, so again, so it should start with I plus 1, because you are at ith row, you want to go down, that's why ith row, comma, till where you should go till rows. Okay, that's what I am writing over here. Okay, and now you should check one more condition. If matrix of, okay, whatever element is below that, and you have to check for that. If that is not 0, then you swap. If it is 0, then you keep on moving. Okay, if matrix of ji, you have to say jith and ith, because it's ith pivot. So j comma I, this is equal to this is non-zero. Okay, so what should you do? Then you should swap. I hope this is clear till here. So if you see what I did is we have tried to find the pivot element. So if it is 0, we are trying to swap the row so as to make it non-zero entry. Okay, so swap the row. So how to swap the rows? There is very easy way. So matrix. Okay, we have to say we have to check. We have to do this. So we have to find ij and we have to replace it with ji. So how to do that in Python is very easy. Ij, and you have to swap it with matrix of ji. Okay, basically you are changing the jth row with ith row. You are swapping the ith and jth row. So and if the swap happened, then you should break. Basically you got the pivot. Now you have the non-zero pivot. If not, then you keep on doing it. Okay, then the second thing is you have to knock off these values. You have to eliminate now. Okay, once you have this, so you are in the rows. That's why I'm making sure that this for loop, I'll write one more for loop over here. So this is one thing, and the second thing is I'll write over here. Now eliminate the things. Elimination step. Elimination step. So what you have to eliminate? Whatever the below entries in the pivot. Elimination step. So whatever is the entries below pivot element. So you have to make them 0. So how to make them 0? You run one more loop, but you run it from ith, the current row you are at, and then go down. So but it should be inside this. Okay, because we're in the rows, and in that we have found a pivot, and we have to go down for let's suppose j in a range of, now this is j, comma, and then we have to put sorry, this is I plus 1, because we are going from I plus 1, comma j. Okay, you can see this, comma row, sorry. So because we have to go to the end of rows. And now we'll keep on swapping. The first thing that we have to is to find a factor. So let's suppose here, if you see in this matrix the 4 is there. This should be multiplied by 2. So this factor should be first known. So how to find this factor is, so you go to this element, okay, go to this element and divide it by this pivot. So 4 divided by 2 is 2. So our factor is 2, and then you multiply with that with the equation. So I'll have to find factor. So how to find the factor? Okay, so how to find that factor? I'll go to matrix of ith j, because that thing basically if that is there, so that thing is my if you see, that thing is my pivot. So I'll go let's say if that is non-zero. Once that is non-zero, then I'll move. Okay, and I'll first have to check, then I'll find the factor. If before doing this, I'll have to check that if that thing is non-zero, otherwise it doesn't make sense. If matrix j comma I, okay, so j comma I should be non-zero. Okay, so entry over here, so you should make sure that entry while you're looking for, it should be non-zero, and then you can basically find the factor. So how to find the factor? Take that entry and divide it by divided by the pivot that you currently have. Okay, so you say factor is equal, and I'll take the current element matrix which was non-zero, comma j comma I. Okay, that is the j in that row, jth below the pivot, the element, and if it is non-zero, and then what we should do is we should divide it with matrix, and then you should say I comma I. Okay, because that's the pivot element. I comma I is the pivot element. And then what you do is, once you do that, you multiply this factor with the equation that contains the pivot, with the row that contains the pivot, and subtract it from the next row. Okay, basically jth row. And now what you can do is, once you have done this, so we'll say matrix of j, that means the jth row in that matrix. So let's suppose you are at here now, so you want to take whole of this and subtract from it this factor multiplied by that equation. So I'm saying from this subtract, so I'll say minus equal to, and subtract from it matrix of, so what's the matrix? That matrix should be matrix I, but it should be multiplied with the factor. Okay, factor multiplied with that, okay, till here we saw elimination. So now the matrix is changed. So if I return this matrix, let's suppose this is my return matrix, so it should be lower triangular matrix, return matrix. Okay, let's do that. So I'll just write a matrix, and I'll write an augmented matrix. So here if you see, okay, so this is my matrix. So this 2 4, I have stacked the b onto it, and I want to actually check what is the solution. So right now the solution should be lower triangular matrix, and I'll write this, print the solution. Okay, let's do it. If you see clearly, you can see that this is a lower triangular matrix. You got zeros over here. Okay, I hope this is visible, so you can clearly see. Let me just put like this, so you can clearly see over here. So these are the 0 entries, 0 entries, 0 entries, and the rest are non-zero entries. So this is a lower triangular matrix. Now after this lower triangular matrix, what you should do is you should do the back substitution. Okay, so for back substitution, what I'll do is I have, let's suppose, 3 equations. I'll create x, y, and z. I'll create solution of this. So I'll say solutions is equal, I'll create a empty or zeros array. So I'll say solution is equal np dot zeros, because I want to return the solution. Solution is where I'll write values of x, y, and z. Oops, so this thing over here, this is back substitution step. Okay, this is back substitution. Okay, now how to do back substitution? You should again run from you should basically run from backwards now, because backwards is where you got the last element. So last element directly will be the value, because at the end you just have one element and you will give the values. You'll perform the dot product with whole of that x, y, and z and give the answer. So if I write that directly over here, so I think you should be able to figure it out what this code does. Not very difficult to find. So I am running this loop reverse. So I am saying row minus 1. Okay, minus 1, minus 1. I am basically coming backwards. So solution of I. So I am giving the solution of that thing. Let's suppose solution of I, it will start backwards, and the first thing that I'll find is answer. So if you see, I perform a dot product of matrix from I to that minus 1. I am selecting that and performing the dot product with the solutions. Okay, and then I am taking this matrix of I minus 1 and subtracting it and dividing it by the pivot element to get the solution. Okay, these are my solutions. Okay, pretty easy to do this, and just pause the video over here and think how does this back substitution is working right now. Give me a second. Now if you run this, we should get the solution. So how to, we just don't need to just print solutions, because solutions is a sort of an array, is a NumPy array of zeros, and in which we have written the solutions of x, y, and z. So I'll print it like this with the f strings. So if you see print solution, solution of 0, solution of y, because the solution is minus 1, 2, and 2. So now if I print it, this should be solution. This is minus 1, 2, and 2. Okay, this whole thing over here, this is used by most of the packages. If you see NumPy, if you see, let's suppose, PyTorch, if you see MATLAB, all these things use some sort of elimination method. Like they have to implement, if they have to implement the elimination method. Now the point is that, why was I showing you this? The point of this whole thing was that if you know something in theory, so you should be able to translate it into code. Okay, so it is very easy to do something by hand, but you have to talk to machines in order to do something from the machines, because this is so generic now. I can give any matrix and it will give me the answer back. Okay, so that the thing that I wanted to inculcate by showing you this example, and you should expect more of this coming in the assignments, is that you should be able to translate the theory into the code. Whatever you know, you should be able to translate that into the code, and that is a good skill to have. If you know how to talk to computers, you can preferably do what are the things that you want to do with the computer. Okay, you should have that algorithmic thinking. Okay, you know something in theory, how to translate it into code, and then talk to the computer. That's what we showed in here. And the assignments will be something like, it will be much more probably advanced than this, where you will have to write the algorithms of linear algebra, and you will have to have the solutions of this. Okay, and this probably might be a buggy code. I am not checking for the these cases. Okay, but I think you people got the point. The last thing that I want to add is this. So here the answer now is minus 1, 2, and 2. This is the answer. Okay, this is our x values for x. So now if you see this, so the initial equation was ax is equal to b. Now we got the x values. Okay, so what was the a? Let me write that coefficient matrix. I suppose it will be somewhere here. So it is 2, 2, and minus 2, 2, 4, sorry, 2, 4, and minus 2, and 4, 9, and minus 3, and this is minus 2, minus 3, and 7. This is my a. Okay, and now x is equal to minus 1, 2, and 2. Okay, so what we can do is, so basically this thing is telling me take one of this, okay, and take two of this, and take two of this to land at b. Okay, what is our b? So our b is 2, 8, and 10. So our b, if I write it, so b is equal to 2, 8, 10. So if I just write this linear combination, so if you see this b is the linear combination of columns of a. So I'll just write it like this. So minus 1 multiplied by 2, 4, minus 2, okay, plus 2 multiplied by 4, 9, and minus 3, and plus This is 2 multiplied by minus 2, minus 3 and 7. Now if you add these things, if you see this is minus 2, so this over here is minus 2, minus 2, minus 4 and plus 2. So now this will become 8, this will become 18, this will become 6, minus 6. Okay, and now this will become minus 4, this will become minus 6, and this will become 14. So now if you add this minus 2, 8 and minus 4, it should be 2. Okay, now you see minus 4, 18 and minus 6, this should be equal to 8. And now this 2, minus 6 and 14, this is equal to 10. So you saw that we got B over here. Okay, so basically whatever this B is, so when we have the right values of X, so right values of X are telling, and then you take the linear combination of the columns of A in order to land at B, because now we got B by first converting. So now theory is this, so AX is equal to B was this, we performed transformation to get UX is equal to C. Okay, and from this we got X, so we solved it for X after elimination and back substitution. Now if you use this X and substitute it here, so now by the factors of X you take linear combination of columns of A and you will land at B. Okay, that's the meaning of this. So if you see the row picture, so row picture was take linear combination of this, this was the columns picture. So column picture was take columns of A and take the linear combination according to X. Okay, and you will land at this B. And what was the row picture? Take these different planes and then move them around and just back substitute them, and then you will see that you don't, basically you are just keeping that point and you are moving the planes around and you are getting the values accordingly. So I hope that you understood a lot of algebra. So there is a lot to come. In the next lecture also we'll keep our discussion on the eliminations, and now I'm going to stop recording over here.